Hey everyone, welcome back to the Summer Pi series, and in this video we're going to train the convolutional neural network that we built in the last video. To start off, let's define the necessary variables. So we have the number of channels, which is 3 because we're working with colored images. There's 3 channels, the RGB layers. We need the number of feature maps, which we'll set to 64. And we'll need to set a number of epochs to train for, and let's just do 100 for now. By the way, if you haven't already, make sure you go to your settings and you turn on the hardware accelerator to GPU. So that way you're training on the GPU for sure. Next, we're going to instantiate our neural network. So we're going to assign a neural network to myCNN, where we pass in the number of channels and the number of feature maps. So as you could see here, we named it convolutional neural network, and we need the number of channels and the number of feature maps. So that's how we instantiate our convolutional network, which I'm just going to call myCNN. And then to make sure that we're using parallel processing, we're going to need to put the CNN on the GPU. So myCNN.CUDA. Next, we'll need to define the optimizer, which defines how we step towards the global minimum. So we'll use the Atom optimizer again. It's adaptive, it's reliable to use in almost any deep learning model. So learning rate 0.002. I don't remember how many zeros there should be, but let's just try that. Criterion, again, we're going to use the binary cost entropy loss. So now we have pretty much all the elements to start training a convolutional neural network. What we want to do next is just to make sure that it's able to run on our data. So if you remember before, we loaded a sample batch. So let's try to feed that batch to our CNN. So let's say myCNN sample batch. Convolutional neural network. Not defined. Oh, I need to run everything, I guess. Okay. Now we're back, making sure that our CNN can accept this batch, and it looks like it can. Okay, so I figured out what it is. First off, remember that our batches load this dictionary, and it contains multiple types of information, so we need to make sure to access the correct one. So I'm gonna just test it out on the lensing images. And then we also need to be careful with the indentation here. It looks like it was inconsistent earlier. It should be at 2 spaces from my code at least, and then 2 spaces after defining the forward block for the return. Yeah, because it ran and it didn't mention any error on the indentation, so make sure you're very careful about that. And then let's not put the CNN on the GPU yet, just because we're going to test it on the data first. So let's run that, and yeah, the CNN does work on the sample batch, so that's a good sign. We could move forward before we make any more mistakes like what we just did. So let's uncomment this. We can move our CNN to the GPU now, and let's start to train it. Let's start to train our model. So the process is really similar to when we built our fully connected neural network. So what I'm going to do is I'm just going to grab the train test code that we made before, and we're going to modify it to fit our model. So the input, the thing is we have dictionaries now, so the batch that we feed in as our input will need to access A for the A inputs. We'll have to access B for the B inputs, and so on. Make sure you do this for the labels as well. Okay, so now I extracted all the information and gave them their own variable names from the batch inputs. And I also added a dot float here just to make sure that it ends up as a float value that PyTorch is able to use. So now we're just gonna need to pass in all this information to the GPU so we could train on the GPU. So we're gonna say if torch.CUDA.is available, we'll put in A and in B onto the GPU. Now that everything's on the GPU, we could start to make predictions and generating some losses. So let's say predictions on the lenses require the input of the lens images. And then the error A, the error on the lensing images, is calculated by comparing the predictions on A and their respective labels. And let's just do the same for the regular galaxy images. And then what we could do is say error equals error A plus error B. We just combine the losses because this is our batch and it's valid to just add the errors together. So if our mode is train, we're gonna zero our gradients, we're gonna backpropagate, and we're gonna take a step to optimize our weights. Again, this is something we've done before. And then, yeah, I think, so the problem here is that when you return predictions, we don't really need the predictions here, so I'm just gonna leave it out for simplicity. But now we have our train and test method. So now let's move on to train our neural network. So again, training this neural network will be very similar to what we did in the fully connected neural network. So let's just copy and paste this block of code from the LSST series. We're going to want the train losses, we're going to want the test losses, but one key difference here is that we're using mini batches. We're doing mini batch training. We went over that in a previous video. And this time, every epoch means that you've trained on every batch, every mini batch that you've created. So for every epoch, we're gonna say for batch in train data loader. So train data loader loaded all our batches for us. We're gonna say train loss equals 0 because we're gonna add them up as we're going through each of the batches. Same thing with the test loss. What we did is we didn't return the prediction, so we could remove this. We didn't even use it last time anyways. We could remove train Y because, as you could see here, our labels are inside our inputs and we just extract it, so we don't even need the labels here anyways. And then our inputs are the batches. And I think this is it. And what we're going to want to do is we're going to say train loss plus equals, we'll say batch loss plus equals batch loss. We're going to add all our losses together because we're just combining the losses for that epoch. And then we're going to append that total train loss onto our train losses so we can make a graph of how the training's going. We'll do the same thing for our test data. So this time the mode is test. We don't need the optimizer, and then we have to say criterion equals criterion test loss plus equals batch loss, and then append your test losses. And that's it. I think we print the epoch that we're on and the train and test loss at that epoch. And let's try to run it. Let's see what happens when we train. Let's see if we called it. I called it epochs here. Let's just call it num epochs because I said for I in range num epochs. So, oh, also one thing, actually the indentation is correct, so that's fine. Now let's try to train our model. Num epochs is not defined, but it's because I changed it up here without rerunning. Okay, we don't need this anymore. What happened there, that error happened because I put my CNN on the GPU, but the sample batch is not on the GPU, so it's not able to calculate it. And now let's try to train my NN. Change this to my CNN this time. Okay, now it's training. As you could see, it started at a very high loss and it's very quickly gone down to even less than 0.1 error. So let's just wait for that to finish and let's take a look at the graph that we generated. So the losses became very small. They went below 0.001 and it's fairly smooth, not that much noise. Usually with mini batches, you have a lot of noise. I can't really tell if there's overfitting, maybe a little bit. Actually here, the test loss is, you could tell it's way higher than the training loss. So we could see that there's some trouble with generalization. But again, we have a small data set. This is something that you might have to deal with if your data set is limited, such as the one we used here. But regardless, we're still getting pretty good losses, something that we could be comfortable with. And yeah, we trained our neural network to classify gravitational lenses with a pretty impressive accuracy, I would say. In the next video, we're going to compare the performance of this CNN versus other architectures. So you could also perform image classification using the fully connected neural network that we did previously. And then we could also combine the convolutional neural network approach with the fully connected neural network. And that's something a lot of people used to do in the past. And we'll try that, see how that compares to the fully convolutional. So I hope you enjoyed that. We were able to classify gravitational lenses with a pretty good accuracy or pretty low loss. And we'll try some comparisons in the next one. So I hope to see you there. Peace.